Okay. Now the question is whether or not it'll upload into the TechSmith relay and then into Canvas. So whole numbers, you know what a whole number is? A whole number is like 1, 2, 3. It's a number on the left-hand side of the decimal, or a number that if it has a fraction with it, is the number that's not fractionized. So fractions are when you've got a number less than a whole number, and when a fraction is used, it's more than a whole number. So we got proper and improper fractions. So something like 1/2 is proper fraction. Something like 3/2 is not. That's an improper fraction. So if you have an improper fraction, it basically means that you've got a number that can be reduced down to a smaller number, or to a more proper number. So 1/2 is basically the same thing as 3/2. If the numerator is greater than the denominator, you've got an improper fraction. So decimal, you know what a decimal is? That's anything. It's basically a digitized version of a fraction. So whenever you have a decimal that's less than a whole, like you have 1/2, 1/2 is 1.5. And whenever you have a decimal that's more than a whole, you know, that would be 1.5. 0.5 would be 1/2, which is less than a whole, and 1.5 would be 1.5. So calculations of a percentage. All percentage is a fraction, so it's a part of a whole. The whole would be represented by the number 1, and then anything above that would be your percentage above. So 1.1 would be 110%. Somebody says give 110%. That's what that would be represented as, is 1 being the whole, 0.1 being, you know, greater than that whole. So 110% would be 1.1. Again, 50% would be 1/2 of something, so it's just a fraction. So 1/2 is less than a whole. 1/2 divided by a whole would be the whole divided by 2, so it'd be 1/2, which would give you your percentage, which is 50%. So to calculate a percentage, you just need to set it up as a fraction, divide the numerator by the denominator. So 1/2 is the same as 0.5, which is the same as 50%. So 10% is 10% of a whole, which is just a small fraction. All you got to do is move the decimal point. 10% is the same as 1/10. So where it gets confusing sometimes is whenever we're talking about 10% of something and increasing by percentage, and whenever we're using percentage and decimal to represent something different. All right. So if we're talking about 10% of something, and 10% is 0.1, then basically you're looking at a multiplication problem. So anytime you're multiplying by 0.1, what's your rule of thumb? 1 times something is always that something, right?
Yeah.
So if you move the decimal point 1 place to the left, and you've got 0.1, what's your rule of thumb for multiplying by decimals? Your result, or your total, has to be what? If you've moved your decimal place 1 place to the left, what are you going to have to do when you multiply everything out? Move it 1 place to the left, right? So 10% of 250 would be 250 times 0.1, and that's the same thing as 250 divided by 10. So 10% of 250 is 25. So we have a tendency sometimes to confuse what's greater than and what's less than in percentages, or even in decimals sometimes. So 12%, is that greater or less than 10%? If you have 12% of something, that's 0.12, it's going to be greater, right? So 12% of 250 would work out in the same ways, either way that you want to do it. Either 250 times 0.12 will give you 30. 250 times 0.12 is the same as 250 divided by 12. Or is not necessarily the same thing. What would you get if you divided 250 by 12?
Probably not 30.
No, you get 20, right? So the setup, you know, it works here, but what you're going to be better off doing, unless you're working on something like 10%, is to, rather than divide out, multiply 250 times 12. Okay? So that's confusing point number one, is that sometimes it's a little more difficult to divide than just multiply by the decimal. So incidentally, 12%, 10% of 100 is 10, right? 12% of 100 though would be more like 80, right? 8 times 12 is 96, so it'll be 8 point something. All right, so 30% is what percentage of 250? Again, we do the same thing. It'd be 250x is equal to 30. So x is equal to 30 divided by 250. X is equal to 0.12. So then 24 is what percentage of 300? You got a calculator on you? Excuse me. I'll take it. It's not COVID. If you remember this time last year, I lost my voice in the first semester because this is not a natural thing for me to run my mouth this semester. So what is 24 is what percentage of 300? Nine?
I'm just combobulated.
My answer not up there. Mine either.
Yeah, it should be 8.
8.
Where'd you get 9?
We're done.
Did you say 9?
Oh, I said I'm bad at math.
Oh, I thought you said 9.
We're done.
No.
How did I hear 9 out of I'm bad at math?
Because we're wearing masks.
Yes.
All right, so percentages can be greater than 100. So 105% of 50 is naturally going to be larger than 50. So you run into a problem that says that you've got 105% of something, then it's going to be the 100% is your whole, right? So 105% is going to be greater than your whole. So 105% is 1.05, so you multiply 1.05 by 50, that's going to give you 52.5. Your whole was 50, right? 105% of the whole is going to be larger than the whole, so it's going to be 52 and a half. It's going to be slightly larger. So 75 is what percentage of 50? It's half again as much as 50. So 50 divided into 75 will give you 1.5. So it's 150% of 50. All right, so percentage of is usually a specific quantity, and maybe more or less than a whole. So 100% of 85 is 85, right? Because 100% represents a whole. 50% of 100 is half. Half of 100 is 50. So 110% of 50, though, is that more or less than the whole?
More.
It's more, right? So it's 10% more. 1.1 times 50 would be, excuse me, 110%. So increasing by percentage is where it really gets kind of confusing for students sometimes. If I increase the class average on a test by 5%, what would that mean? You scored a 90. And I said, okay, I'm going to add 5%. Yeah, it's going to increase, right? So if you increase by a percentage, that means it's going to go up. So sometimes we'll have a tendency to confuse increase by a percentage with a percentage of. So what is, okay, you scored 100 on the test, we'll make it easy. I said I'm going to increase by 5%. What's your new score? 105, right, so you increase by a percentage, you've gotta add the original back in, right? So you got 105%. As opposed to percentage of, if you score 105, that 5 is what percent of your whole? Added 5%, right? So percentage of would be the 5%, but to increase by a percentage, you've got to do you've got to calculate that in one of two different ways. You've got to either account for the whole and the percentage in your multiplication. In other words, you scored a 100, I'm going to multiply that by 1.05, right? That will give you 105. Or you can multiply it by 0.05 because that's what I'm increasing your grade by, but you've got to add the 100 back in, right? Because if you score 100 and you only get 5%, that's not increasing by 100. That's failing you out of class, right? So increase by percentage, you've got to add the original back in. All right, so this is the example. Class average was 80 and increased by 5%. So what that would be is 4 points on the class average. So the class average is now how much?
84.
84. There you go. Yep. So you have a whole, you want to know how much to add to it. Add the original value, increase by 85 by 15%. So you could do that in one of two different ways. Either you, and this is a step you're usually going to miss, 85 times 0.15 would give you roughly 13. Where you're going to have a tendency to stop is right there, but you're increasing by a percentage. So you got to add that 85 back in and it bring you to a 98. Or I find the easiest way to do it is to just go 1.15 and it'll give you the result right there. Okay. The third way, and you've got to know your calculators, you know, because some of your calculators are set up a little bit different. What you can do is 85 plus 15%. And some of your calculators, when you hit the percent sign, it is as if you hit the function key plus a zero, or plus the equal sign. Like this one, let's see, would be 85 plus 15%, oops, 85 plus 15%, it brings it right up. But some of your calculators don't take that step, okay? This one came up to 97.75. Some of your calculators, you have to hit the equal sign afterwards, okay? So some of your calculators will, if you hit 85 plus 15%, it'll give you that, but it won't give you the total until you hit the equal sign, okay? So know your equipment. If you're increasing by percentage, if you're increasing by percentage, then your total is going to be higher than your original, right? So in this case, if you had a calculator that didn't total it out with the equal sign, you hit 85 plus 15%, and it gave you 12.75. Is that greater or less than 85? Yeah, it's less than. So you know you got to add the 85 back in. So go ahead and hit the equal key, and it should bring it up. So again, when increasing by percentage, the original value has to be included, either added in prior or after the calculation, multiply, you know, by 1 point something. The addition method works just as well. It's just that you cannot forget that additional step. You gotta, make sure you include it. All right, so increase by a specific percentage. In your packet or in your textbook, should have book. There it is. I don't think that this references the textbook. I think this is actually your packet information. So. It just refers back to that previous slide. So if class average was 80, and I curved it about 5%, that would mean that your class average went up by 4 points. So how would you work a 200% increase on original value of 85? You have 85, and you need to increase by 200%. What is 100% of 85? 85.
Just double it.
That's the mistake you're gonna make. Okay, so you're increasing by 200%. Your original value was 100, so you already have 85. Okay, but you're increasing, okay, let's say you increase by 100%. You've got 85, you increase 85 by 100%.
Oh, so it's already, that's gonna double it.
Bingo, that's gonna double it. So what is 200% gonna do?
Quadruple it.
It's gonna triple.
Oh.
You,
Yeah.
okay? So this is probably the most common mistake on the math quiz is when you increase by like 200%, you're gonna have a tendency to say, well, that's 2 times. And it is 2 times. Your increase is 2 times, but your total is
3 times.
3 times. Right.
Okay.
Okay? So you're increasing by 200%. You've already got the 100% of 85, but you're increasing by 200%, which is twice of 85. So again, you've got to add in the 85. So how would you work that out in a multiplication problem? Multiply by 3, right. In the addition problem, you'd multiply by 2 and then add in back in the 85, right? So if I increase my mass by 300% when my original value was 400, we got a big one, right? What would I do? What would my new mass be?
1,600.
1,600, right? Alright, so that just works through everything we just talked about. So don't confuse 200% of, which is what 170 would be, with the increase by 200%, which would be 255. Excuse me.
Wait, go back, what was the answer?
On which one?
The 85 by the 200%, what was the final?
255.
Okay.
Okay, now to decrease by percentage, everything just kind of changes around. So decrease by 15%, then you can follow the same steps. 85 times 0.15 gives you the same 13, so 85 minus 13 is going to give you 72. All right, so notice you're not going to have the 1.15 because you're not increasing by, you're decreasing by. So if you're using your calculator, and you can use a calculator, it's just those, basic function calculators, then use the same thing. So 85 minus 15% is going to give you 72.25. So rounded to 72. So don't confuse 15% of with decrease by 15% either. Your 15% of is your 12.75. Your decrease by is going to be your 72.25 or 72. All right, so let's go in the opposite direction. We're going to decrease 250 mass by 35%. So 250 times 0.35. And then again, subtract 87.5 from 250 is going to give you 162.5 mass, or you can use the function keys, 250 minus 35%. All right, so now we have decreased mass to 35% of the original value, and that is just stopping at this point right here. So you've really blasted the patient with way too much radiation, and you need to cut your technique back to 35% of what your original value was. Then you would just multiply 250 by 0.35, and that will give you your 87.5. So when do we use the 15% rule?
If you want to keep the same exposure.
When you want to keep the same exposure, you change KVP, and in the opposite direction, you change your mass to compensate for the change in KVP. So when you want to change your exposure, you want to change your scale of contrast, but you want to you want to change your scale of contrast, but you want to leave the exposure essentially the same, right? Remember, density and exposure are essentially the same thing. Density in screen film radiography was, you know, just the overall darkening of the image. In screens and films, we refer that in CR and DR, we really refer that to the exposure index number. So you're going to change your KVP and your mass. When you want no change in your index number, but you want to change your scale of contrast, what do we do to increase contrast? What does increased contrast mean?
You wanna increase your KVP.
You gonna go down in it?
Okay, so I got a up and a down. What does increased contrast mean? Just the word. Increase black and white, right? So you want to increase the black and white, which, how does that relate to grayscale?
It's gonna be less grayscale.
It's going to be less grayscale, right? So it's going to be lower contrast. So we're dusting out all these words again. It's going to be lower contrast. So if our intention is to increase contrast, what do we need to do with our technique, or with our KVP? Do we need to decrease it, or do we need to increase it?
Decrease.
Decrease it. You decrease it so that you get more absorption, less penetration, and your contrast increases. So increases in KVP, decreased contrast, decreases in KVP, increased
I
contrast.
thought it was inverse.
Yeah, and you will. That's why we go over this so many times. That's why we go over this there's nothing in the curriculum we cover more than imaging, you know, because it's so confusing. Increase grayscale, decrease contrast, you know, just, it's confusing. So changes in contrast, changes in density or exposure. If we change KVP only, if we increase KVP and that's the only thing we do, what happens to our image, according to the literature? Decrease contrast, we increase KVP, contrast goes down. And what else? And the only thing we did, we're not using 15% rule, we just changed KVP.
Double the mass.
It effectively doubles mass. You know, it doesn't really double mass, it increases the exposure. And I think that's kind of where you were going with that. Yes, it's effectively the same as doubling the mass, right? It increases exposure. If the only thing that we do is increase KVP, contrast goes down, exposure goes up. Okay? So we'll change KVP only when we want to change contrast and we want to change the index number. So if we want to increase our contrast and change, the index numbers on different machines go in different directions. Most of them, as the exposure goes up, the index number goes down. Some of them, as the index number, or as the exposure goes up, index number goes up, which is logical. But most of them go in the opposite direction. So I hesitate to say, you know, index number, you know, goes up, but exposure, when you increase your KVP, density goes up, exposure goes up, probably going to bring your index number down on most machines. If you decrease your KVP, then contrast goes up and exposure goes down. Not necessarily your exposure number, but your exposure to the image receptor goes down. Okay, so original technique is 80 kVp, 32 mass, and you need a shorter grayscale. What does shorter grayscale mean?
Higher contrast.
Higher contrast. How do we get to higher contrast? Lower KVP, right. All right, so when you're reading these test questions, take them one thing at a time. You know, the original technique, 80 kVp at 32 mass. You need shorter grayscale. Stop right there. Okay, shorter grayscale. Get it figured out before you go on. Shorter grayscale means you're going to decrease your KVP and less density. Okay, so if you decrease your KVP, contrast goes down. What happens to exposure?
Wait a minute, say the question again.
Oh, I'm sorry, I just said this backwards. Original tech, decrease KVP, your grayscale, you get a shorter grayscale, your contrast goes up. What happens to your exposure? It goes down, right? So, what's this asking you to do? You get a shorter grayscale, which means you did what with KVP? Shorter grayscale, you decreased, right? So you decrease KVP, and it said that in your decrease in KVP, you got less density. Is that natural for just a change in KVP? So what's going to happen when you decrease your KVP? Yes, it is. So what's this question asking you to do? Is it asking you for 15% rule? Or is it just asking you to reduce your KVP?
It's just asking you to reduce your.
Bingo, right. So just, understand the question before, because a lot of times what you'll do is you'll read halfway through it and you'll say short grayscale, 15% rule, decrease KVP, increase mass. No, pay attention to the rest of it. You decrease your grayscale plus you've got a reduction in density or exposure. So it's just a change in KVP. So this particular question would be asking just for a change in KVP. So if your original technique was 80 KVP, you wanted to increase your contrast, what would you do in this case? And you wanted less exposure.
15%.
You'd use 15%, but you wouldn't change your mass, right? 15% rule automatically assumes you change your mass. This is not changing your mass, so technically this is not 15% rule. You're going to reduce your KVP by 15%, but what are you going to do with your mass? Nothing. Right. You're going to leave it alone. So, same mass, you reduce your KVP down to 68 KVP. And all that is why, that happened. Decreasing KVP gives you a higher contrast, decreasing KVP without adjusting mass, you get lower exposure, you have fewer photons produced, less scatter radiation, less penetration. So, you know how to calculate mass. MA times time gives you your mass. Your textbook actually has this thing flipped over, and I'm not real sure why it does that. Because it looks like a basic math problem with mass on top. To calculate your mass, your overall mass, what you would do is divide, or either your MA or your time, is you would divide your mass by one of these two factors to get the opposite. So why it is in the book it's flipped around, I don't know. It's kind of weird. So, we're not going to spend a tremendous amount of time on calculation of mass, but sometimes what you'll run into is questions on what would be probably single-phase timers. So they read out fractions, right? So what I find the easiest thing to do to work out problems, mass problems, when we have a fractional time, is to convert that to a decimal. So what that would be is the same as dividing 20 by 3/15 of a second. 3/15 of a second is the same as 0.2. So 0.2 divided by, or 20 divided by 0.2 would be 100. So I find it easier to calculate by changing a fraction to a decimal point than working with a decimal point rather than working with a fraction itself. Okay. So, in the previous example, what MA and time would be used if half the exposure time were to be desired? So you want half as much exposure time. So, obviously you're not going to have that right in front of you on the quiz. So what you're going to have is essentially just the question. In the previous example, what MA and time would be used if half the exposure time were to be desired? Okay. So what we had was 20 mass, and we found out that we had 100 MA station, right? Because we calculated this out. So if on the next adjacent question you had this, in the previous example, what MA in time would be used if half the exposure time were to be desired. Okay, so what is it asking?
You wanna cut the time in half.
You want to cut the time in half. Does it say anything about density, contrast, anything else? No. So it's only asking you about about exposure time. So what do we call it when we can adjust MA in time to come to the same mass? It's a law of, goes back and forth, reciprocity, right? So we're using the law of reciprocity. So if our objective here is to arrive at a shorter time, maybe the patient's breathing, maybe we got a Parkinson's patient or whatever, and we need a shorter exposure time, but we need the same exposure. It didn't ask you to change any kind of exposure, so you got to assume that we're utilizing the same mass. So we reduce our exposure time from 0.2 to 0.1, so we cut it in half. But in doing that, what do we have to do with our MA?
Double it.
Double it, exactly. All right. So again, in the previous example, what MA in time would be used if a 1 second shallow breathing technique. So you're using the same technique, but now you've got a situation where maybe you're shooting a sternum. So you need the patient moving, you need to utilize the patient's motion. So you need a 1 second exposure. So again, we'd be using reciprocity. So we would decrease our MA station down to 20, and we'd have a 1 second exposure to again arrive at 20 max. All right, so ratio and proportion. A ratio is a relationship between two numbers indicating how many times the first number contains the second. So 1 to 1 means that all things are equal, right? They're identical. 2 to 1 means that the first is twice the size of the second. 1 to 2, it flips everything around. The first is half as much as the second. It's really just a division problem is all a ratio problem is. All right, so like grid ratio. What is grid ratio? It's the height
Yeah.
of the grid strip divided by the distance. What distance? Distance between, right. So, it's been a while since we talked about this, so don't confuse distance between by the thickness of grid strip, right? It's the distance of the interspace material. So it's the height of the grid strip divided by the distance in between them. So, generally expressed as 8 to 1, 10 to 1, 12 to 1, 16 to 1. You can have 3 to 1 and 5 to 1. Some of your pediatric hospitals will use very low ratio grids to save the dose of patients. So they generally use a 5 to 1 and whenever they can. So it's the height of the grid strips compared to the distance in between them. And it tells us how much lead is in the grid and how effective it's going to clean up scatter radiation. So 8 to 1 means that there's 8 times the height compared to the distance between the strips. Strips are really stacked right on top of each other. 16 to 1 is even more than that. So more lead, more cleanup, more effective grid. There's a couple of different ways that we can get to a higher ratio grid. Like if we took an 8 to 1 grid, so just using numbers that we can kind of wrap our heads around. If we've got an 8 to 1 grid and our grid strip is 8 inches tall, right? And it's 1 inch in between each one of the grid strips, so the interspace material is 1 inch thick as opposed to 8 inch tall grid strips. We got 8 to 1 grid, right? So if we needed a 16 to 1, we could do that in one of two different ways. If we needed to get to a 16 to 1, basically what we could do is use the same interspace material and increase the height of the grid strip to 16. Wouldn't that be 16 to 1? But what if, instead of doing that, what we did was we kept that 8 inch tall grid strips, but we took that interspace material and instead of 1 inch, it's ½ inch. Would that not do the same thing? Okay, so a lot of different ways to get the grid ratios. In the second example, what changed? Another grid characteristic changed by narrowing that grid strip. What would that be? Not grid ratio, but grid oftenness, grid frequency. There you go. Grid frequency increased. By increasing the size of the strips, nothing changed in grid frequency, but by narrowing that grid strip, we increased grid frequency. All right, so make sure you're comparing the right things. 8:1 and 1:8 grid are very different things. So some ratio problems compare two ratios. Transformer laws is an example. Turns ratio on the primary side versus turns ratio on the secondary side. You know, remember that? No, you don't. Has Tran made y'all draw the circuit yet? Ooh, it's coming. It's funny too.
Like we have to like
She
draw it,
shows
like,
me. She
I
shows me.
just
It
like
breaks my
drawing.
heart. I spent a whole semester up here drawing that thing. 1 year later, you don't know anything. Anyway,
I
somebody
blamed
drew
it
a
on
turtle
the first
one.
day whenever you told us that we didn't even take notes, and I drew out the entire circuit. You're like, you didn't have to do that. I'll blame it on that. I should have finished it.
This is true.
I should have finished it.
You were the one that drew like, I mean, it
I was
looked
taking
like
notes.
art.
I was taking notes the entire first lecture, and you're like, you don't need those, so I stopped taking notes. So if I draw it and it looks terrible, I'm blaming it on that.
Oh, yeah. Oh. It's not the drawing that's bad, it's that, you know, people just can't remember the parts, you know, you got something over here and something totally disconnected over here. Like I said, one year somebody drew a turtle, couldn't remember anything, just drew a turtle. Come on, you didn't even try. All right, so magnification, calculation of magnification is just ratio problems. So what we're controlling there, or what we're comparing there, are SID and OID. Field size is another. So what we're comparing in field size is the size of the field, basically the collimator versus the size of the field, projected field size. So when you're comparing two ratios, make sure that you compare equal things. So to make sure that, like on your projected field size, you want to make sure that you align on both sides of your equation the same variable. Okay. So like if let me just I hate to do this. I'm gonna pull them up over here. Now the lights are gonna go on. Let's see if I can. Control system is off. You know what? We got more boards back there. So when you view this at home, this is gonna make you sick. You gotta have to move more than that.
Oh,
I'm still trying to figure this thing out, so.
you use
All right.
this side or this side?
Right there. All right, so make sure that whenever you're setting up a ratio type problem, the most important thing is to make sure that you're comparing apples to apples. So field size. We got field size. What we're going to be looking at is the difference between the field size as it leaves the collimator and the field size on the image receptor, the projected field size. So what you've got are four different things. You got a distance from the focus to the aperture, or where the opening is, you know, be it an aperture diaphragm or collimation. So you've got a distance from here to here, and then you've got a distance from here to here, and then you've got this distance versus this distance. Okay, so you got four distances you're gonna compare, right? And it's a ratio type thing, so, you know, the colon is replaced by, because we're gonna actually try to figure this thing out, is replaced by equal sign, right? So what you're comparing is, or what you're trying to determine is, you're gonna be given three of these four measurements. So let's say we've got an opening size of 4 inches. And that opening size is 10 inches below the focus. And let's say we've got a SID of 40 inches. So what we don't know is that, okay? So what we're gonna do is, in this case, this is jumping ahead a bit, but the easiest way to set this up is big over big is equal to little over little, is the easiest way to remember it. Okay, so what we're talking about is we've got 2 long distances and 2 short distances, okay? So our big distances, we've got a big here and we've got a big there, right? So what we want to make sure that we do is we keep like things across from each other. So we've got a big measurement and a little measurement. We want to make those the same. We want to compare like measurements. So when we're looking at those, what are the like measurements? What is most like this distance?
4.
Yeah. This distance here, right? So the 4 inches. So we got a little over here. So we got let's say, well, we'll just do it like this. 4 is equal to, and what am I going to put across from the 4?
X.
X, right. So those are my big and little for that. Okay, so I need a little measurement in the opposite dimension. So what's that going to be?
10.
10 is equal to, what's going to go right across from that?
40.
40, right. So now how do I solve that?
Cross multiply.
Cross multiply, right. So 40 times 4 would be 160 is equal to, 10x. 10x. Divide both sides by 10. Both sides by 10, so x is equal to 16, right. Now here's the thing about ratio problems. It doesn't really matter how you set them up, providing you're comparing the same things across from each other. What I mean by that is, what if we invert this whole thing and we go 40 over x is equal to 10 over 4. So we cross multiply. 40 times 40 is 160 is equal to 10x. So x is equal to 16, right? Now you start comparing apples to oranges, and what you're going to have, I mean, both of these are the same, right? But you start comparing apples to oranges, and you got, let's say, x over 40 is equal to 10 over 4. Is that going to give you the same result? No, not by a long shot. You got 4x is equal to 400, x is equal to 100. So make sure that you keep everything across from each other. It doesn't really matter which way you go with your bigs and your littles, as long as you're comparing the like objects across from each other. Does that make sense? So ratio problems. Back around. Hot?
It is hot in here, but I'm fine.
Eli, you can see if you can drop that a little bit.
It's like
Ah.
42.
Yeah, I need it to be negative 700.
Negative something.
So high.
So all of that just, is really kind of magnification the same way. They're ratio problems, so as long as you flip the entire thing, you should be good. Just walks through the same thing again. Still, same stuff. All right, so area of a circle. How do you calculate area of a circle? It's pi r squared. What you're going to have a tendency to do, the mistake you have a tendency to make on the calculation of a circle is you're going to be given maybe the diameter, and pi is assumed, so 3.14 is always going to be a factor. So the area of a circle, you may have a problem that says you've got a circle that's 10 inches in diameter. What was the area? So how would you find that?
It would just be pi times b.
Hmm?
It would just be pi times b. If you have the diameter.
Pi r squared. Right, so diameter is, all right, so if you got 10, okay? So you got 10, the area of your circle is 10, right? So what is radius? Or I'm sorry, the diameter is 10. What is the radius? Half of 10, right? So half of 10 squared is
5.
25. 25, right? So it would be pi times 25. Now, so what you're going to have a tendency to do on the test, on the quiz, is to take the diameter and multiply that by pi. Well, that doesn't get you there. You got to take the radius, which is half of the diameter, and square that and multiply that by pi, right? So, so the area of the circle, the diameter is 12 inches. What you would do is divide 12 by 2 and then square that will give you 36, and your area, total area would be 113 square inches. How do you find squares and rectangles?
You just multiply the size.
Yeah, just length times width. So if you got a squared, 10 by 10 square, it would be 10 times 10, would be 100 square inches. If you had a rectangle, it'd be 10 by, the short side times the long side, so it'd be 10 by 12 in this case, it'd be 120 square inches. So scientific notation, I'm going to be, on the test, on the quiz, I'm not going to be extremely particular about this, but you got to get close. And generally on the quiz and on the test is actually multiple choice, but on the quiz, if it looks like I know what you did and you were on the right track, and maybe you had a difference in rounding between what you did and what I have on the key, I'm going to give you credit for it. So likewise in scientific notation, if you're really pretty close, then I'm going to give you credit for it. So an amp, scientific notation is just a means of using a relatively small number to represent a very large number. So an amp is 6.241 times 10 to the 18th power electrons, and that is a massively cumbersome number to have to draw out. So scientific notation just even though that's still a lot of numbers right there, compared to drawing out 18 zeros, that's really pretty insignificant, right? So in writing scientific notation, what you're going to do is you're going to put the decimal after the first significant number. In this case, it's going to be the 6 times, or 6.241 times 10 to the 18th power. So you would count the zeros and everything coming up to the decimal point, and that would be your times 10 to the 18th power. So really what you would have is 15 zeros out here for the actual number of electrons you would have. So it'd look like that. So big number, right? So what would be our scientific notation for this one right here? How would you write it?
It's 10 to the second.
Good.
7.42 times 10 to the 11th power. Okay, so negative, scientific notation going the opposite direction. In this case, 1 would be our first significant number, and now we've got to count in the opposite direction. So 1 being our first significant number, what we would have is 1 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how will we write that out?
It would be 10 to the negative 10 power.
Very good. 1.23 times 10 to the negative 10th power. There you go. Metric conversions, just kind of down and dirty on this. Really, what we're going to be calculating on the quiz will be your kilo. We're not going to worry about hecto or deca, deci, centi, and milli. And the rest of them are just FYI and OG stuff. There is a calculation between centimeters and inches, and make sure you pay attention on the quizzes, because it may change. It may ask you, you got an area that's this big, and it gives you a readout in centimeters. What are the square inches or whatever? So there are 2.54 centimeters in an inch. So a centimeter is a little bit more than a half an inch, but 2.54 centimeters per inch. Kilo means 1,000 times. Deci is 1/10. 1/10. Centi is 1/100, and milli is 1/1000. So 1 second equals 1,000 milliseconds, and you're going to have a tendency to move the decimal in the wrong direction on these. You're going to kick yourself for it, but probably right up there with the most commonly missed questions on the quiz. So a millisecond is very small. 1 millisecond is very, very small. So 1/1000th of a second is what we're talking about there. So conversion of seconds to milliseconds, move the decimal places 3 places to the right. So if we have 1 millisecond, that's 1/1000th of a second, move 3 places to the left. So how many milliseconds, 0.07 milliseconds is how many seconds?
0.0000.
There you go, 0.000 is the conversion, 0.7 seconds. So 12 milliseconds would be how many seconds?
0.00012.
30 and then 12, 0.00012 seconds. Right, so on the quiz, sometimes, people have a tendency to move this in the opposite direction, so you've got 0.07 milliseconds, so they'll say, well, that's 70 seconds, okay? Remember, milliseconds are tiny. They're milliseconds, 1/1000. So if you're converting from milliseconds to seconds, the number is going to have to represent something very, very small. If you're going from seconds to milliseconds, on the other hand, you have 0.07 seconds, then what's your millisecond equivalent of that going to be? It's going to be tiny.
If you're going from seconds to milliseconds?
Seconds to milliseconds.
Yes.
So 0.07 seconds is going to look like what in milliseconds?
0.00007 milliseconds.
That's where you're going.
Oh,
That's
you're
what
going
we
to
just
the
said
right.
was
It's
milliseconds to seconds. Now, if we're going from seconds to milliseconds,
Okay, it's gonna be bigger.
So it'll be
it's going to be bigger, right? But that's what you're going to have a tendency to do on the test. You're going to have a tendency to flip those around. So seconds to milliseconds,
Be small.
It's gonna be small.
yeah. Or milliseconds to seconds is going to be small. Seconds to milliseconds is going to be larger. The number is going to be larger. It's going to be essentially the same thing. So 0.07 seconds is going to be how many milliseconds? 1, 2, move 3 places to the right. It's going to be 70 milliseconds. 0.12 seconds is going to be how many milliseconds? 1, 2, 320 milliseconds. Okay? So if we have fractions converting to milliseconds, now we've got to convert fractions to decimals and then convert to milliseconds. So 2/5 of a second, we've got to convert that to a decimal first. So 2/5 divided by, or 2 divided by 5 is going to give you 0.4. So it's 0.4 seconds. But how many milliseconds is that? You're going to move at that point the decimal place how? 3 places to the right. So you got 1. There would be 1 0, 2 zeros, 400 milliseconds. Right? Same thing down here. Convert the fraction to a decimal. From the decimal, convert by moving your decimal place 3 places to the right. All right, temperature conversion. There's some problems in the workbook that you can work through. There's even some in D'Angelo's that you can work through. The biggest issue with temperature conversion, in my experience, is that we have a tendency to want to set them up the same. We'll say Celsius to Fahrenheit is 5/9 times Fahrenheit, Fahrenheit minus 32. So Celsius to Fahrenheit is Fahrenheit to Celsius. So Celsius to Fahrenheit naturally is going to be 9/5 times Fahrenheit plus 32, and that's just not going to work. Okay, so make sure you set them up properly. Remember that in most cases, the number in Fahrenheit is going to be larger. There is some places they kind of switch places, but if you're above freezing, really not even just above freezing, but if you're in a comfortable temperature, the number in Fahrenheit is going to be significantly larger than Celsius. 100 degrees Celsius is what? What can you do at 100 degrees Celsius? Boil water, right. What does it take to get to that in Fahrenheit? What's that? 212, right. So 50 degrees Celsius, is that comfortable?
Yeah.
Probably a little warm, right? 50 degrees Fahrenheit?
Cold.
Yeah, it's
That's perfect.
not a little bit chip.
Not cold.
You're begging for 50 degrees right now, right?
Heaven.
So, the quiz, the first quiz, no, I'm thinking physics. Okay, so you may have to convert Celsius to Fahrenheit, Fahrenheit to Celsius. Just make sure you get them set up right. And how you're going to know is if you're in a normal range of relatable temperatures, most of the time Fahrenheit's going to be larger. Once you get down to freezing, what's freezing in Celsius?
0.
0. What's freezing in Fahrenheit? 32. Yeah. So most of the time, unless you get really, really low, the number in Fahrenheit is going to be higher than the number in Celsius. All right. We did finish by now. Any questions?
So is all the stuff you just went over in that booklet, that packet that's
Yeah.
out there?
Yeah. It's a, kind of the student version like what you had last year.